Are CO2 PRVs different? Is the question I've asked here. The answer is not necessarily. Subcritical CO2 doesn't really behave any massively different from any conventional refrigerant. So although we at Henry have a high pressure range of valves specifically designed for CO2, all of our valves, even our low pressure ones, are suitable for CO2 because at your subcritical side, low pressure end, normal valves can work fine. But transcritical has its unique challenges. The obvious one's increased pressure. I've put here 130 bar because again, that's where our limit is on our pressure relief valve range, but I've heard up to 150, 160 bar in some systems, which again has the impact as a valve designer. You have to look at the rigidity and the structural integrity of the valve at those pressures. A thing that comes in consideration there is the seal material as well. You tend to find most high pressure CO2 valves are Teflon or a derivative thereof in the seal material, whereas at lower pressures you can get away with softer seals with better leak tightness because again there is not as much force acting on the seal because the valve's not set quite as high. Increased temperature obviously goes hand in hand with the pressure as well. Again, that comes back to affecting the seal material. Make sure the seal material is appropriate for the temperature range it's going to be working at. Again, I've put 150, but again, you could even get higher than that. Again, the other consideration from a design point of view with temperature is the spring, because if the valve is in a high temperature environment and you haven't selected the correct spring design or materials or pre-stressed it enough, it can actually lose tension due to the temperature over the life of the valve, which makes the valve open early, which obviously is something we don't want.
Welcome to this CO2 Experts event. So excited to be here again, 2025. Starting off the year great, loving what's going on. 2025 is going to be a great year for the refrigeration industry, CO2 industry. And today I got a special guest. But first, I want to talk about some of the things that we've been doing already at CO2 Experts. We've already had experts from all around the world. You do really want to get and rewatch some of these videos, get to the YouTube channel. If you're listening to it on the podcast, go and watch the video because there is lots of great slides, getting into selection software like today we're going to dive into, and really invest in yourself. That's what it's all about, is investing in your knowledge so you're better tomorrow than you are today. And this is what we do here on a daily basis at Refrigeration Mentor. And if I say anything for 2025, invest in yourself. So welcome to this CO2 Expert session. Today I have a special guest, Jordan Gronkowski. Gronkowski.
Either is fine.
Jordan Gronkowski, and he is a pressure relief valve expert. He works for the Henry Group. We're going to dive into it a little bit deeper, but we met back at Chilventa, and we stopped in and I had a conversation because honestly, I know what pressure reliefs are. I know what they do, but it's something that we don't understand enough. Well, a lot of people that I talk to in my circles, we know that if you have a catastrophic event there to protect the system so you don't have an explosion or you don't have something blowing up realistically, because these are vessels with refrigerant or some sort of chemical inside them, and ours is refrigerant, but you have these pressure reliefs to stop these catastrophic events. So sizing is key. We know in CO2 transcritical systems, we have multiple pressure points. So on the transcritical side, you can have one pressure relief. On the flash tank receiver or the vessel, you could have one size pressure relief. On the low side suction, you could have a different size pressure relief. All depends on the design of the manufacturer. And the manufacturers today are doing a fantastic job. They're working with Jordan and his team at Henry and coming up with the best solutions for their designs. So if you're working with one of the top CO2 manufacturers, because there are many of them from around the world, they are adding these to their systems. But us as technicians, designers, and engineers, we really need to understand, what should the actual size be? Is it going to be safe? What is the code in our area, what country, state, or province are in? If you have any questions, please throw it into the chat because we got a lot going on today. If you're listening to on the podcast, please leave a review or share this with someone. This is how we grow the knowledge of our industry. That's what we're trying to do here. Uplift the knowledge of the refrigeration industry. Jordan, welcome to CO2 Experts. How you doing?
I'm good, Trevor. Thanks for having me on, and thanks for the invite.
Well, I knew I wanted to have you on for sure. We met in October, and we had some great conversations. So you can go and check out on LinkedIn a couple of videos, or on the YouTube channel on a few quick videos we have in there. And we learned about the different trees, pressure relief trees or trunks. I'm not sure exactly the proper terminology, but we'll find that out today on protecting CO2 systems, because we know CO2 systems run at a higher pressure, right? And we need to make sure they are safe. And I'm excited to dive into it a little bit deeper with you, Jordan, because you're an expert. How long have you been working with pressure relief?
Since I left university, probably around 18 years or so ago now, further back than I care to admit. But yeah, it's been my the focus of my working life. It's how I started in industry, was developing a range of new PRVs and a new methodology how to design and introduce this new range, which was successful. And then after that, it's kind of grown arms and legs from there. And obviously, as you mentioned, CO2 in that time has really taken off as a refrigerant, especially here in the UK and Europe, and in America now as well. The North America, it's starting to take off. So yeah, it's an exciting field.
So I want to ask you a question. What are the biggest thing that you see? Because you're an expert at this, right? You've been doing it for 18. You've been designing, you've been sizing, you've been in the manufacturing process, you've been doing it all. But what do you feel or you see that, say, manufacturers, designers, and even like technicians and contractors are missing on that? Because like I talk with you, I'm kind of ignorant of the pressure relief valve over the years. Like I'm better now. I understand codes from around the world. I understand the value because it's safety. You know what I mean? It'll relief if the pressures get too high. But what are some of the things that you see that people are missing the boat on within their knowledge of pressure relief versus of having this specific knowledge that like most of us should have?
One of the biggest things, although it is getting better, but one of the things that comes up a lot is somebody looking to fit a valve to a vessel, and they have for instance, a 1/2-inch MPT threaded connection, and they just want a 1/2-inch MPT valve to fit onto the connection because it's the right thread, so it must be the right valve. But obviously, that's as we know, that's not the case, and it's very important that valves are sized correctly because as you covered, it's really a last line of defense against something catastrophic happening. So if you have a valve on there that's too small for the vessel, then it's not going to stop the pressure from building beyond the set limits. But equally, if you have a valve on there that's too large, it's not going to behave properly either. So although people see them as very simple devices that they have to put on a system because the code says so, there's a lot more to it, as we'll get into today.
So and we might get into it in some of the slides you have, but let's talk about that right there. Like if you have an oversized valve, so because in Canada here, our B52 code states that after every 5 years, I believe, they need to be inspected or replaced. Okay, and I think that's around the world, like it's similar code. So you need to understand the code in the country you're in. But if all of a sudden you need to replace it and you see it there, and they put one that's too large on, and because you just said it may work erratically, what if someone puts a too large PRV on a system?
Yeah, so we refer to that, the code refers to that as gross oversizing of a valve. And what can happen there, and we'll get into a little bit more on the slides, is that when the valve is too large, effectively, if you can imagine, you've got this, I always think it's easier to imagine things if you accentuate it. So you have this huge valve in this tiny vessel. As soon as that valve opens, there's all the gas is going to shoot out the vessel almost immediately because it's such a large valve, and the valve will immediately close again. But then what happens is the gas from the rest of the system creeps back into the vessel almost again immediately, and then that'll open the valve immediately, and then it'll evacuate everything in the space, and then it'll close. And the cycle continues until the valve is what we call chattering, where it vibrates very quickly. And it's a horrible thing to hear as well. It sounds terrible. And if you can imagine, a lot of the valves have things like PTFE or Teflon seats, and this hammering of the seat against the seal destroys it. It can, in extreme cases, it can actually take the seal out altogether, and then you have a valve that, sure enough, it's closed, but it's leaking because you've destroyed the seal.
And so, did you say that term was chaffing? What was
chattering? Chattering.
Oh, chattering. Okay, teeth, yeah, chattering. Yeah. No, and that makes sense. Yeah, I'm excited. Yeah, so let's share some slides. So if you're listening to on the podcast, make sure that you key in, take some notes, get over to the YouTube channel and watch the video too.
Right, so we're just going to dive in to this relatively short presentation on CO2 PRVs and safety devices, challenges, selection, and a little bit of troubleshooting at the end there as well. Now, Travis, as I said to you, Trevor, feel free to jump in anytime if you have anything you want to highlight or to...
Well, for sure. I'm sure I'll have lots of questions.
So what we're going to cover, first off, some specific challenges that CO2 gives us as valve designers. It's interesting to know what these are. Then we'll look in a bit more detail at the selection or how to correctly select a PRV. Now, I'm going to focus on the European standard, EN 13136. You've got the ASHRAE, I think it's ASHRAE 15 in the States. I think it's ASHRAE 15. And again, the two are becoming more and more aligned. I think the ASHRAE standards are becoming more like the EN standards as things get revised. So although this might not be specifically applicable to you guys wherever you are in the world, it's all the same theory. So it's good to know.
And that's a big thing. I want to point that out. I already said it. It's like depending on where you're at in the world is going to be different codes and regulations. And you may, because I had a friend here, Robert Nash from Copeland, send out, and I was asking about the pressure relief, and he says per ASME B 31.5, the system is to be tested at 1.1 times the design working pressure. But that's going to be different maybe here in Canada, maybe in the UK or Ireland or wherever you're at, you know what I mean? Or Scotland. And this is important. You could be in Australia, you could be in New Zealand, you could be in South Africa. The codes may be different. And then in your province, like in my province or state, it could be even stricter depending on your local jurisdictions. Okay, yeah. So this is very, very important. As us, even as technicians, you need to understand, and you might be thinking, why does this matter? The designers are supposed to do that. At the end of the day, as a technician, we're responsible for the system, not the engineers or design. Because we're working on it, because it could be 2 or 3 years down the road. So just remember that if we're the last one to touch it, we're responsible for this stuff. So it's important to understand the codes.
Yeah, certainly is. So yeah, after we talk about the selection, we'll have a little look at the Henry Online PRV selector that we got, but it takes a lot of the hassle out of the selection process. Again, you might have seen Trevor and I covering that at Chilventa last year, one of the videos. Then we'll look a little bit at pressure drop, which is important consideration as well. Pressure drop into the valve, but also coming out from the valve and how that can affect behavior. And then a little bit of proactive troubleshooting, I've called it, at the end of the presentation. So the first thing to look at is CO2 challenges. So obviously, as you guys know, CO2 with the conventional refrigerants on your diagram, you tend to be in this kind of region here. With CO2, you're up here, so you're beyond the critical point. You're at much higher pressures, much higher temperatures. So what challenges does that give us as valve designers? So are CO2 PRVs different? Is the question I've asked here. The answer is not necessarily. Subcritical CO2 doesn't really behave any massively different from any conventional refrigerant. So although we at Henry have a high pressure range of valves specifically designed for CO2, all of our valves, even our low pressure ones, are suitable for CO2 because at your subcritical side, low pressure end, the normal valves kind of work fine. But transcritical has its unique challenges. The obvious one's increased pressure. I've put here 130 bar because again that's where our limit is on our pressure relief valve range, but I've heard up to 150, 160 bar in some systems. Which again has the impact as a valve designer. You have to look at the rigidity and the structural integrity of the valve at those pressures. A thing that comes in consideration there is the seal material as well. You tend to find most high pressure CO2 valves are Teflon or a derivative thereof in the seal material, whereas at lower pressures you can get away with softer seals with better leak tightness because again there is not as much force acting on the seal because the valve's not set quite as high. Increased temperature obviously goes hand in hand with the pressure as well. Again, that comes back to affecting the seal material. Make sure the seal material is appropriate for the temperature range it's going to be working at. Again, I've put 150, but again, you could even get higher than that. And again, the other consideration from a design point of view with temperature is the spring, because if the valve is in a high temperature environment and you haven't selected the correct spring design or materials or pre-stressed it enough, it can actually lose tension due to the temperature over the life of the valve, which makes the valve open early, which obviously is something we don't want. And the final point I put on here is rapid decompression, which is a term that is quite well known in the oil and gas industry, where the temperatures are much higher again. It's effectively, for those of you who maybe don't know, it's effectively what in a phenomenon where an elastomer seal, like an O-ring or something, the gas, because of the high pressure, can effectively creep into and impregnate that material. And then when it's exposed to atmospheric pressure or low pressure, the gas bursts out of the material very suddenly and effectively rips it to bits. So in a relief valve, if you're using again elastomer seal in the seat itself and the valve opens, you can see this rapid decompression, which is why again choice of material is very important for a CO2 valve, especially transcritical. So jumping into the selection by calculation method. As we've touched on, I'm sure you guys all know, and we've mentioned already, that the most important thing with the PRV is that it is your last line of defense. It needs to be sized correctly. If it's too small, it won't protect the system. If it's too large, as we discussed earlier, you get chattering and issues. So there are many standards, again, depending on your local province, country, area. What I'm focusing on here is EN 13136, which is a European and British standard, which we use constantly here. Again, even though there are many different forms of standards throughout the world, you'll find that if you comply with something like a recognized standard like 13136, it tends to be acceptable in most places, or it can be easily modified to the needs of another standard, for example, North America. So 13136, it looks at 3 scenarios that you size your valve based on. It. External heat source, which is effectively a fire, by far the most common one that everyone thinks about when they're sizing a PRV. Internal heat, which I don't see used a lot, that tends to be the scenario where you would maybe have a heater coil or something inside your system, and you're worrying about that running out of control and adding heat that way, excessive heat that way. And compressor flow being the other one. So again, typically for transcritical CO2 systems, we sometimes see valves located on the discharge line, and they will be sized to cope with the flow rate of the compressor. So if there's some blockage further down the system, the valve will open and allow the total flow rate of the compressor to be discharged. And the standard then says that you should consider as many of these as are applicable, and you should obviously use the worst case for what valve to pick. So there's some calculations involved, which we'll dive into in a sec. They require system properties, refrigerant properties, and PRV properties, obviously, as well. And basically, you're looking at 2 terms. You're calculating a required flow rate, the QMD, as it's called. This is what's required to keep the system safe in these scenarios. And you're then calculating QM, which is the actual rated flow rate of the valve. And effectively, you're making sure that you make sure the valve has more rated flow than your requirement. So find the required flow rate is the first step. So as I mentioned, you've got your 3 scenarios here: external, internal, compressor. Looking at external heat source, this is the equation that we use. Again, I'm going to be throwing some numbers and equations up. There's not going to be a test at the end.
There will be a test. There will be a test.
That goes back to something that one of my lecturers said to me at university, was that you don't necessarily have to remember all this stuff, but you have to know that this stuff exists.
Yeah. It's
important to know that there is this in the background, and that's why it's important to calculate these things. So external fire, here's your equation for QMD. You've got the surface area of the vessel. If it's a simple tank, then it's straightforward enough. If we've got something like a condenser, you use the boxed area, if you like, rather than taking all the surface area of the fins. It doesn't work if you do that. HVAP is the heat of vaporization, which is taken at 1.1 times the Z pressure. And then you've got the Greek letter phi, which is the density of heat flow rate. Again, that is given in the standard as 10, but it may vary if you've got things like insulation or things on the vessel. Internal heat source, very similar equation, but you have the same heat of vaporization, but you also have this rate of heat production term, which again comes from the heating element or whatever you're using in that scenario. In compressor flow, really what this equation is doing is working out the flow rate of the compressor in kilograms per hour. You're looking at the volumetric flow, which are kind of these terms taken together, multiplied by the rho, which is the vapor density, and the base V, which is the volumetric efficiency of the compressor.
So a question on these different calculations. You're trying to figure out the kilograms per hour or pounds per hour or SCFM, depending on all of them. How do they how different are they? When you do these calculations, we're not going to get into the calculations too much, and I know your software does all this stuff, but how do they differ? Because maybe they will change faster, I guess a fire versus someone shuts something on the discharge line. How do these? Is that what it really is?
It depends on the system. So if you might have a system where your receiver, so your external heat source, you're using your receiver as the calculation, is maybe average size, but you maybe have 3 or 4 compressors feeding the system. So in that case, you would find that your compressor flow would be the one that will drive the selection of the PRV because it will be much larger.
I get you.
Conversely, you might have a small one compressor system, but you might have a huge receiver, in which case this will come out as the worst case, and that's what you use for the.
Now I get it. Now I definitely get it, because depending on the design of the system will depend on the equation you have to use, like the components in the system.
Correct. The standard does say you always use all of them, or as many as are applicable, and then pick the worst one. But you can usually tell, and most of the time it's the external heat source that people use. Again, as I said, this, except from what we typically see on transcritical CO2 systems, are people using PRVs on discharge lines, and then it's obviously the compressor because it's not even connected to the receiver; it's coming straight from the compressor.
That's right. Yeah. Well, I learned something there.
So you've got your QMD, if you like, your required discharge. Next, you find the right PRV. So here's another equation. Again, lots of terms in here, but this is the equation that tells you what the rated flow of the valve is. And again, as I said earlier, QM, which is the valve flow, must be greater or equal to QMD, which is your requirement. So you just go through the terms here. C is a function of the isentropic exponent for the refrigerant, which you get in the standard for many. It can be derived from the isentropic exponent itself. Again, if you can't find it in the standard or anywhere, the refrigerant manufacturer can usually get that to you. A is the flow area of the PRV, which again, the manufacturer will have. This KDR term is specific to the European standards, and it comes from the certification of the valve when it's flow certified. Although it's specific to European standards, we at Henry, our valves are dual certified to both European standards and the ASME standards in America. And we therefore flow test our valves at the national board in America, and we get a rated slope, which is, again, one of the kind of terms that we use from the American side. But we can derive KDR from that. So even if you have an American valve that's totally just set to certified on slope, you can again derive this KDR term from the slope. KB is what's called the theoretical capacity correction factor for subcritical flow, which is a bit of a mouthful, but effectively that is always 1 if your valve is supersonic internal flow, which all of these refrigerant parts generally are. So you generally don't need to worry about that term too much, unless you have a strange valve. P0 or P0 is the actual relieving pressure, which is 1.1 times your set pressure plus atmospheric pressure. And the final term there is your nu naught, which is the specific volume of refrigerant in meters cubed per kilogram in the terms of the units here. But again, you can get other units.
Yeah, so there's a lot there. You know, this is engineering stuff. This is design stuff. This is stuff that Jordan knows inside and out. And this is the behind the scenes where a lot of you here that are engineers and designers understand this stuff. But as you know, for a technician to size it, all this is done. You don't have to worry about this. This is done in the software, the selection softwares. It's all inputted in there. But it's very important that, like Jordan said earlier, is to understand that this is what's happening in the background.
Yeah. Correct.
Because when I look at that, Jordan, I'm like, oh man, that's above me. That's for sure.
And that's kind of the point of this a little bit as well, is to show how easy it is using our selection tool. That you don't have to anymore worry about. In the olden days, you would have had to get the pen and paper out and go through this, which I've done many times.
Well, I see quite a few people on the call right now who have definitely done it as well. So
yeah, good stuff. Good stuff. Okay, so that was the selection process basically. So just to summarize, establish your QMD, select the right PRV to meet or exceed that in your QM. And this is where I've mentioned about gross oversizing that we touched on earlier. There is no definition given in the standard about what gross oversizing is. It just says not to do it or to avoid it. We, based on some research we've done and some independent research have found, we tend to typically classify gross oversizing as 5 times. So if the valve has 5 times the flow of the required flow, then we would call that grossly oversized. And that's where this shatter and seal damage we talked about earlier can come in. A couple of other sections of the standard just to make you aware that it's there. Variations in the phi term, which was the density of heat flow rate. Again, if you've got insulated vessels and things, that term can vary a little bit from the 10 that is stated as recommended in the standard. Liquid expansion is a little bit of a different beast compared to gas, because obviously gas is compressible, liquid isn't, so it behaves slightly differently. You do need to make sure if you're fitting a valve on a liquid line that you use a valve that is rated for liquid discharge. Henry valves are all rated for gas discharge only, so it shouldn't be used in the liquid line. You do get special valves that are rated for liquid. Again, subcritical flow, as I spoke about earlier, most valves tend to be critical flow through the valve itself. So that term doesn't mind. But if you have a different valve, then the manufacturer will probably advise that you use a different term. And a little bit, we'll talk in more detail later about the adjusted PRV discharge capacity QMD dash. And the pressure drop calculations, which are a whole other branch of calculations and things that I won't get into in too much detail here.
So before we move on, so these are different standards within the code for, okay. So let's just talk just quickly, because we know CO2 systems need to be insulated very well because they run colder, a lot of moisture, and can cause rust and deterioration and stuff. So there's a lot of insulation on there. So when we talk about various insulation, do you mean actual, like you said, they're insulating of that flash tank receiver or that vessel that will change the selection for the PRV?
It may do. So remember, if we skip back a slide, what we're doing for the external heat source method here is we are looking at the surface area of the vessel and various other terms. The reason we're looking at the surface area of the vessel is what this calculation is trying to figure out is if there is a fire in the plant, how quickly is the heat going to be absorbed into the vessel? So that's why it's worried about surface area. Rather than, a lot of people think it's the volume of the receiver that matters, but no, it's the surface area, because it's how quickly the heat's going to be absorbed in, because that will determine how quickly the pressure and temperature is going to rise inside the vessel. Therefore, how quickly, how much capacity the valve needs to have to vent that safely and stop it getting above a certain like 10% over limit. So if you have insulation, then that's going to affect how quickly the fire heat will be absorbed into the vessel.
Yeah. And so just to put that in terms, I guess you have say a lighter, and you put a lighter on the bottom versus you have a blowtorch putting on, or you know what I mean? So it's which you don't do, but that you're just getting more heat on it quicker. And so now with that variation, so we're talking about the first requirement, but with the insulation on, because a lot of times it's 1 inch, 1.5 inch, even up to 2 inch insulation on some of these vessels, that will change the sizing and selection of the PRV.
It could do. It changes that term at the top. My Greek letter's correct. That's 5. Yep. So this is given in the standard as a value of 10 as standard, but it does say you should account for insulation. It'll go up or down depending on type of insulation, level of insulation, etc. And because it's the top line is multiplied by that, it's going to have quite a big effect. So yeah, it could well change the selection.
Yeah, that's cool. No, it's something I would not have thought of.
Right, where did we get to? Selection method there. Let's get through this. Other sections, we talked about that.
So the liquid, and let's get into the liquid inspection. So this is important. We need to make sure that if it's gas PRV, it needs, if it's on the gas line, so discharge line, suction line, it's gas. But if it's in the liquid line, you need a different design. And why is that? Is it just because you need more flow because liquid's denser or whatever like that? Does it need to be bigger? Like, can you just give just a little insight on the difference between a liquid and a vapor one again? I mean, you might have
so from I mean, again, we don't make any liquid valves at Henry, so it's something that I've dabbled in, but I wouldn't say I'm an expert in. But fundamentally, liquid and gas behaves differently, especially flowing through a valve where, if you look at the fluid flow and the aerodynamic, or fluid mechanics, I should say, inside the valve, you're getting really high accelerations of flow in very, very short spaces, changes in temperature, changes in pressure. You can get what's called cavitation in liquid, where it'll, it basically, it doesn't behave like a gas, without going into too much detail.
Yeah, and then with CO2, you get dry ice. So that's you know what I mean. So all of a sudden it's blowing out liquid and then it just stops. You know what I mean? That's an issue. So okay, I totally understand that. Okay. I don't think I've seen, honestly, on a CO2 system. I'll have to dive in a little bit quicker if I ever seen any on the liquid line. I don't think so. Like, they will usually pump back into like a vessel or something, and then a vessel would be gas. So yeah, I'll have to look into that.
Yeah, it's maybe more for conventional refrigerants, as you say. So so okay, move on. Anything else on that page you want to pick up on, or okay?
Let's keep going.
Let's go. So some complexities specifically for CO2. So eagle-eyed amongst you will have noticed that HVAC and nu naught are calculated at saturated conditions at P naught. But obviously with transcritical CO2, we're not at saturated conditions, we're above the critical point. So what if, in this case, P naught is above the critical point, which is your supercritical CO2? So this is what the standard says, but to paraphrase effectively, if that is the case and you're above the critical point, HVAC and V naught shall be taken at the critical temperature minus 5K. So when you look at your refrigerant properties, you go down 5K from your critical temperature, and that's where you take these values from, regardless of how high the pressure is. What if the temperature is above the saturated temperature? So you've got superheated gas. Then again, the standard gives you this, which effectively says that if you have a superheated gas, then HVAC shall be taken at saturated conditions. So again, even though you're to the right of this case of your saturated line, you take the values from the saturated line. You mentioned it there, Trevor, risk of solid CO2 formation in the discharge of the PRV line. Again, that's something that's mentioned in the standard, but again, they don't give much advice as to how to avoid it, except for saying it should be avoided, which is helpful. Again, the advice that we typically give are that ideally outlet pipework should be avoided altogether, and the valve should just be allowed to vent. There are cases where that's not possible because maybe the valve's at, for example, head height somewhere where somebody might be working, and you don't want that to discharge off straight into obviously somebody's face. Could be very dangerous. So if you do need to use some outlet piping to change the angle of the outlet or flow, generally try and use the shortest length and the largest diameter pipe possible. So again, for an angled valve coming out, if all you want to do is point it up the way, then a simple angle that would point the flow up would be better than having to pipe it all the way through meters and meters of pipework to the roof, because that's when you'll get the solid CO2 forming, which is a blockage in the exit of the valve. Again, potentially very dangerous.
So yeah, let's stick on that point, because I know here in Canada, this is why you need to know your code. Different provinces in here have different rules and regulations. So some provinces say that every PRV, depending on the system and depending on what type of room it's in, they need to be vented outside. So now we know CO2 compressors have discharge pressure reliefs on them. So some provinces may say, and depending on who you talk with as the agent who is doing the inspection, may say you need to pipe them all the way outside. And some other ones say you don't need them because you have mechanical vent by code here in Canada. This is something that still is a gray area that is not pointed out in the code. And I'm sure this is other parts of the world as well. It's kind of gray. And depending on the inspector you get, they may approve or disapprove the installation of those PRVs. We know one thing: we cannot have a shutoff valve before any pressure relief. And I know we didn't get into it yet. You cannot do that, because if someone forgets it shut off or something like that, their accident could happen. And then now you got a ticking time bomb potentially. You can't have it them at the outlet, just like Jordan just said. You can't put it at the outlet. It's the same thing. If you shut it, even though the pressure relief goes off, it's blocked. It can't go anywhere. And so this one here is, I talk with designers, I talk with engineers, and I talk with contractors, and it's a gray area depending on where you're at. The best thing possible is to, like Jordan said, not have anything on the outlet and it'd be outside, but that's not the case. There's so many pressure reliefs on systems now. I've seen one that I was at, they had 7 compressors on the medium, 4 or 5 on the low temp, and all of them were headered together into a big, large header to go outside. You know what I mean? And then have one big one go outside. So please just follow up with this. Find different people in your province, state, or country and ask them questions, because they honestly, some of them don't know. Because I've been reaching out to the people that are supposed to know the code, and it's great for them. So follow up, because I did have contractors reach out to me here saying they had to pull out all their installations, or they had to go and repipe the reliefs all outside.
Yeah, it's a challenge.
So it's a touchy area, even with you, because you deal with this, because they're calling you up. Well, what's the code? Well, I don't know, because that area of jurisdiction could be different. Some could say, just like we said, some could say, okay, you can put something at the outlet as long as it's a bigger diameter, just like Jordan said. Some others say, no, you have to pipe the pressure relief and put the pressure relief outside. So this is where you need to work with your local authority.
Definitely. So have we got time, Trevor, to run through a selection online, or do you want me to?
Yeah, let's do it. I think this is important, because let's show how anyone can really do this. If you're in a tech, you're doing an install and you're a technician, you want to understand this. This is very, very important. Or if you're a designer.
Yeah. So across here to Henry Tech website. This is our technical United Kingdom page. If you're on the Henry Tech website and you want to get to it, you simply go to technical, click on United Kingdom, we bring up this. We've got lots of useful stuff on here as far as operating instructions, declarations of conformity, various technical brochures and things. The bit we're interested in just now is the PRV selector here. So I'll just bring this up. And I'll log in quickly. Again, to set this up, you just click the sign up button. You'll get a quick email just confirming your email address, which you click a link on, and then it's a one-time thing. It's free, and then you can log in anytime you like. So first page. So the way it works, you've got 4 different sections, and we just work through them step by step. You first off select your refrigerant. So we're going for R744 for CO2. Again, set pressure. Again, let's go 120 bar. You can enter this in PSI and kilopascals, any of the 3 units, doesn't matter. Next, this is our 3 discharge methods. So this is what we talked about. So we've got internal. There's your QH term, asking you for that. You can click external as well. And again, this is your cylindrical. Is it a box? Do you know the surface area? So you can just override it by putting area. And again, you can use meters or inches, doesn't matter. Here's your density of heat flow rate term we talked about. Normally, this is what the standard said, 10 is normally assumed, but a higher value can be used if necessary. Again, depending if you've...
Okay, let's just talk about that for a second. So just say I have a 1-inch insulation on the vessel. What number would I put in there? And like, is that another calculation? There's another whole calculation for that?
Good question. The standard doesn't tell you. So I don't know.
Okay, that's fair. So if anybody knows,
it's something that it's another, as you say, and there's lots of this you'll find in the standard. There's gray areas where it says you need to do this, and then somebody asks the question, well, what do I do? Well, don't ask me. I'm just the standard. I don't know. So yeah, it's to do it again. It's looking at the density of heat flow rate. So you would have to get a feel for how your specific insulation and the thickness of the insulation affects the heat flow rate into the vessel, which is again, there's no guidance really how to do that in the standard. There may be other standards.
Yeah. So I guess this is where someone would have to go to the insulation company, who designs the insulation, and find out what that fire rating is for that insulation, I'm guessing.
Perhaps, yeah.
I'm just throwing things out there. If anybody knows this, please throw it in the chat. Yeah, reach out to me. I would love to find this out as well, so we can share this knowledge with other people, because I'm really trying to get a lot of these gray areas for people to have a better understanding. We know we'll never get all the gray areas out of standards and stuff, but if anybody has that information, please send me an email, info@refrigerationmentor.com, and I'll try to get this out to the public. So like to the refrigeration industry.
Yeah, definitely. So yeah, external, and then you've got your compressor method we talked about as well, where you can put in all your terms, or again, if you know the volumetric flow rate, you can enter it directly. So again, as the standard says, you should consider as many of these as possible. So you can tick all 3 boxes and use all 3, and the software will automatically then select the worst case scenario and select the valve based on that. For the purposes of today, I'll just use the external method, and we'll just override it with a simple value of 10 meters squared. Next step, again, we'll cover this right at the end of the presentation a little bit. Whether you want any additional components, so I'll tick the boxes just for the sake of an example, 3-way valves and rupture discs, and then we can click calculate, and that takes us to the last page. So what I've got here are all the valves in the Henry range that are suitable. Again, you can see here 5701EX and the 5702 series valves. You've got inlet connection, outlet connection. This is your QM we talked about in the calculation. This is the actual rated flow rate of the valve of CO2 at the set pressure. Again, 3-way valves and rupture discs that fit. If you expand the box here at the top, you get all the calculation parameters. So this is all the formulas we talked through. Here's a reference to the standard, and here's all the parameters that has come out for this calculation. There's surface area that we entered, and here is your QMD. This is your required discharge capacity in kilograms per hour. So this is the requirement, and you can see here 3225. We're getting a valve with 530, and then 8809. The software will not select a valve that is grossly oversized, so you can be confident that even though this is a larger valve, usually you would pick the closest one because it's the most efficient to pick the smallest one, the one that's closest to your requirement. But maybe you've got an inch connection on your vessel and you don't want to have an additional leak path by having an additional connection, so you could quite happily go with a 5702B in this case.
So for an example there, it says external is 3.225 as the minimum requirement. If your actual requirement is 3.3, that would be good, or even 3.225 would be good.
Yeah, so it has to be equal to or exceed. Okay, so yeah, good. As long as there's safety factors in all these calculations anyway. So you can always think, oh, it should always be bigger, but if it equals to it, then it's acceptable. Yeah. And just to point out that that's a comma rather than a point, so it would be 3,225. Yeah, really difficult to see on the screen.
Yeah, sorry, 3,225. Okay, yeah, makes sense.
Okay, so last point is just to, as it says here, connect which one you want. So let's go for the 5701X. Once we click that box, we get more data at the bottom here. Again, here's your formulas that we talked about. Here's all the different parameters of the valve that's come out. Again, we've got the option here to select which three-way valve we want. Just pick that up at the moment. It'll give you some more parameters of the three-way valve, which is important when you look at pressure drop, which I'll do in a second. You can go back by clicking and deciding you want to change something. So say you want to, you've got, oh, I made a mistake there, it's supposed to be 5. You can recalculate. You can jump straight to the end again. Now you can see, because we've reduced the surface area, our requirement is now 1,612 because it's half the surface area. So we've got two different valves. We've got the valve we selected last time, but we've also got the option of the smaller one now, which is 1898. Again, gives you the option to tick all that. Once you've completed this and you've got your selection fine, you could send an email to Henry, but more importantly, you could download, or more usefully, I should say, you could download this as a PDF. So this downloads to your PC, and this is laid out exactly as the standard requires, with all the references, all the equations, and all the information there. So this is really useful because when you put your design of your system together and the notified body asks for the proof that you've selected your PRV collector, you present this bit of paper in your technical file and job done. So it really is a one-stop shop for everything.
Yeah.
So that's that. Again, easy enough to get to. I'm sure Trevor will share the link around for anyone who wants to have a play about with your own selections. And we'll get back to our presentation. So as I said, advantages of Selector, as you guys have seen there, it's pretty user-friendly. It's pretty customizable. You can play about with different figures and values. You can look at different scenarios at the same time. It's in full compliance with the standard. And again, you get that downloadable sheet for your design file at the end. So how are we doing for time? We're getting.
Yeah, we're good.
We're okay. Okay. So I won't spend
important stuff.
I won't spend too much, but I'll try and zip through. But I can't talk too fast sometimes. So slow me down if you need to.
No, I think that's
pressure drop calculations. So pressure drops in PRVs. Why is it important? We talk about pressure drop in the inlet line, pressure drop in the outlet line. Why is that important? So this is a typical straight-through PRV with an angled outlet on the top. This is when the valve is closed. This is the normal condition that the valve will see all the time. Coloring pressure here. So red is high pressure. When the valve opens, this is a simplistic rendering of what actually happens. So as the flow accelerates through various portions of the valve and geometries, it'll effectively, the pressure drops. So you start off with red, through orange into the blues and out the tops. And this is how the valve is designed to behave. What's the effect of excessive pressure drop in a PRV? So first of all, if you've got pressure drop in the inlet or the outlet, there's no difference in set pressure. If you've got a long pipe that puts too much excessive pressure onto the valve due to, when it's flowing, it doesn't change the set pressure of the valve at all. So the valve will still open at the correct pressure. But what will happen is that the valve's forced to close unnaturally early, and it's not operating as designed. So in extreme cases, it's very similar to what we talked about with the chatter, with the oversizing. It can result in seal damage and loss of seal integrity. So to try and visualize that a little bit, for upstream line and components, so you've got things like three-way valves, rupture discs, etc., and just long pipe in the inlet line. If you have a pressure drop in that line because your pipe is too small diameter or it's too long, you've got excessive pressure drop. This is effectively what the valve sees. So where it saw, when it initially opens, again, everything's static, nothing's flowing. It'll open with that high pressure and it'll vent. But then as soon as it opens and the flow starts, that's where this build-up pressure drop starts. And the valve sees a lower pressure. So you notice this has changed from red to yellow. It's seen a lower pressure. Because this happens instantaneously, pretty much, the valve then wants to close again. And then as soon as it closes, the flow stops and the pressure builds up again because all your built up back pressure. And then the valve opens and again, the cycle repeats. Very similar to what I explained before. And you get this chatter. The piston moves up and down and chatters. So what can cause that? Things like rupture discs that are incorrectly sized, three-way dual shutoff valves that are incorrectly sized, and obviously piping that's too large or too long or too small diameter. And again, similar to the effect of grossly oversizing the PRV.
So basically, we're saying that if you have just a rupture disc or the three-way valve is too small, like it's sized incorrectly, that the pressure will build up, it'll open up, but then it'll close too quickly.
Yeah,
is that correct?
It'll close because it's effectively this pressure it sees disappears as soon as the flow starts. Its restriction of flow, it sees less pressure, so it closes. But then the flow stops, so the pressure increases again. Yeah,
because what we want to do with the pressure relief, we want to let out enough so that when it seats again, it's at a safe pressure in the vessel or whatever you relieve from to hopefully not relieve again. Is that correct?
Correct. Yeah, the valve needs to open and discharge. I would call it discharge naturally. A nice smooth hiss of noise as it's designed. If you restrict it in either of these ways, then you're forcing it to close, but it's not ready to close yet. So it wants to open again. And this is where you get the chatter.
Okay. Yep.
So downstream line is the opposite. So you've still got your high pressure at the inlet, but if you have a long, excessively narrow diameter pipe on here, the pressure doesn't drop enough through the PRV because you have all this built up back pressure behind it. And it's the same thing. In fact, from this point of view, it's getting forced closed by the excessive pressure in the outlet. As soon as it closes, that flow stops. So as soon as the flow through here stops, your back pressure disappears because there's no flow, and the pressure is back to atmospheric pressure. So the valve will open again. But as soon as it opens, the flow starts, and you're into the same scenario. So it's the same thing, but on the downstream side. That's usually caused by excessive piping, either length or short diameter. It can also be called, not so much for CO2, but some refrigerants and things like ammonia, where we discharge into a vessel rather than discharge into the atmosphere. That can obviously have back pressure effect as well. You get superimposed back pressure as well. And that's an important point, is that, again, all Henry valves are back pressure dependent. So they are designed and they must relieve to atmospheric pressure. You get some PRVs that are specifically designed to be back pressure independent. Now, they can deal with a certain level of superimposed back pressure, they call it. So they're charging into a pressurized environment as opposed to with charging the atmosphere. So it's important to make sure you get the right valve for the job.
Yeah, and where do you see that more in industrial? Is that where you would see it? In like
things where the refrigerant's specifically nasty or harmful, you don't want it in the environment, you would discharge to a receiver or something.
Yeah, exactly.
So how do we deal with all this, and how do we get our heads around it? How do we know if the pipe's too big, too small, all the rest of it? Back to the same standard again for us in Europe. I'm not sure what the equivalent ASME standards or ASHRAE standards are, but I'm sure that there will be some there. If anybody knows, stick it in the comments. But EN 13136, again, there are calculations in there and limits. So the limits from 13136 are 3% of set pressure on the inlet side and 10% of set pressure on the outlet side. If you have a back pressure independent valve, I think that's 20% on the outlet side you can get away with. Again, for this, if anybody is doing this and they want a little bit of help, Mark, because the calculations for this I'm not going to put the formulas up because they're even worse than the ones before. There is support available from Henry. We don't have it online as yet, but we have an in-house tool based in Excel, which again will work through the various calculations. You can add in different amounts of header lines and things, and it can work out what diameter of pipe you should be, or is the minimum diameter you could use for that. And again, we can send you that as a PDF. So if anyone needs any help, please give our tech team a call. So the last section I just want to run through quickly is the what I've called proactive troubleshooting for PRVs. So mostly it's the safety device kits that you see on screen here. Again, if you saw Trevor and myself at Chilventa, we covered a little bit of this on the stand. So PRVs in general are fail-safe devices. So they are designed so that if any individual part of the valve breaks, they're going to open and vent. So there's no really, from a system pressure point of view, there's not really a safety risk for a PRV failing. So when you're troubleshooting PRVs, it tends to be because you've got a leak, or because there's a defect in the valve that's causing it to leak out. As I say, unless there's something really wrong with the valve, it should not open, if that makes sense.
Yep.
So there's two ways that you can kind of really be proactive in ensuring you're ready to troubleshoot something like this. So the first one here is the three-way dual shutoff valve. So this is the device at the bottom here. Now, Trevor, you mentioned before you're not allowed usually to have a shutoff valve upstream of your PRV for the simple fact that you could block it off. There is scope in certainly the EN 378, the European relevant European standard, for a single shutoff valve in line with an upstream for PRV. But I think it must be under lock and key, and it must be controlled by a certain personnel. But we at Henry don't offer that, because even then, there's still a risk that human error can occur and somebody can forget to turn it off. And so we only offer the three-way valve solution here. And what the advantages of this are that if you have a problematic valve, or even if just a valve blows because you've had an issue, you can switch this valve across and isolate the one that is the problematic one. You very easily, in this case, it's a cap you remove, and you just a little spanner in, and you can change the flow from this angle to this angle. And that allows you to remove the valve that's isolated without any depressurization of your system, any degassing, anything. You just pop the valve off and away. So although, as I say, troubleshooting is such, if a valve is leaking maybe because of chatter or maybe because of debris in the system, there's so many reasons a valve could pass. Being proactive and having this three-way valve in the system means that it's really not going to cause you any problems, because you just isolate across to the other one, remove it, and send it away for inspection.
You don't have to pull out the whole charge to
exactly,
change the valve.
which would be a nightmare.
Quick question
it means you've still got system protection as well. That's the important point. You could do the same thing with a single isolation valve, but then your system's unprotected. So something happens, you have to run away for something, you forget to unlock the valve again, and something, God forbid, happens to the system, it's gonna be a bad one. So this means you're always protected.
So with your three-way valves, is there like can you tell, like, is there markings on there to say, okay, you're the left one's open right now, the right one's open? How do they tell when someone's going to switch it over? Is there?
Yeah, so with this design, I've not got an image on the screen, unfortunately, but with this design, which is our award-winning 9.3 series valves, there is a stem here that you've got a spanner on, and it's got like a little L indication on it, and it shows you which way the flow is going to go.
Okay.
So you can see visually on the end of the stem. The older models, some of our legacy three-way valves are longer valves with a piston that cycles back and forth to shut off one port or the other. And you really just have to look at the stem and see, is it in or is it out? To figure out.
Back seat it or front seat it.
Back seat or front seat, exactly.
Yeah. Okay, cool.
Again, we talked about these devices are things that can introduce pressure drops, so it's important to make sure that the three-way valve you're using is correct for the PRV. Again, we've got guidance in our product catalog and on the online selector, as you saw there. I could select different three-way valves. It will tell you which one is adequate. Because again, if you have a three-way valve that's too small, then it's going to restrict the flow, and your relief valve is going to be affected. So important to make sure you use the right one. And the second thing you can do again for proactive troubleshooting is the second part of this assembly, which is the rupture disc. Now, rupture discs are, for those of you who don't know, a way of hermetically sealing a system, but still having the ability to relieve pressure. So it's a disc in this plate. In this case, it could be nickel, it could be different materials, but it's scored with a laser and very finely tuned so that it bursts at a specific set pressure. And the set pressure of the disc is tied to the set pressure of the PRV, so they both work in unison. The advantages of this are that PRVs, and it's kind of a common misconception, and it's becoming more prevalent as, rightfully so, the industry is becoming more sensitive to leaks and trying to reduce leak rates everywhere. But there's a common misconception out there that a PRV is capable of absolute seat tightness and it should never leak. Now, from a technical point of view, everything leaks. Welded joints leak, so there's always leak there. But when you think about a PRV, and we're talking about welded joints, I think that 3 grams a year is kind of the term in EN 378 that's banded around as being acceptable as leak tight if something's 3 grams a year of refrigerant leakage. And that's talking about welded joints. If you think about a PRV where you've got a Teflon seat and a Teflon seal like a brass or a steel seat, all you're doing is pushing these two surfaces together. Like, that's never going to be hermetically, it's not possible for this to be hermetically sealed. So you'll always get, in every PRV, you will get a small weep, we call it, of refrigerant through, and it's not enough to set off a leak detector. You wouldn't notice it with any detection equipment. But because refrigerant is heavier than air, it sits inside the valve, and not so much with these, but some of the straight through valves where the outlet's on top, the refrigerant just builds up and builds up and builds up over time. And if you go to that with a leak detector, it goes wild and you think you've got a big leak because you've got this pool of refrigerant that's built up. And that causes issues. And if you blow it out with some air and then test again, you won't find a leak because it's not leaking at a rate, but you've got this issue. So the beauty of a rupture disc is that you've got this hard seal. It's a hermetic seal. And what it does is it completely isolates the PRV from the system. So the PRV doesn't even see the gas. So it's the ideal solution because the PRV just thinks it's sitting on the shelf somewhere. So it's nowhere near the gas until it needs to see it, until it bursts. So the rupture disc bursts, the PRV goes at exactly the same time. Obviously, the rupture disc is gone, it's open, so the PRV is the thing that gives you the reseal again. And then you've got it on your 3-way valve, so you can easily switch the valve across, change it in for a new one, and no issue. So those are the two things. Your 3-way valve allows you to maintain valves and switch valves out really easily. And your rupture disc gives you that. It's the only solution that will give you complete leak tightness and give you that peace of mind that there's no weep occurring anywhere in the system.
Yeah. And Stephen threw in the chat, and it's worth mentioning that you should only have one live PRV at a time. So if you're mid-seated, for an example, and the pressures build up, you're going to blow both reliefs, not just one.
You are, and again, I've seen that. Again, it's a information that we need to spread. So thanks to was it Stevie said put it in the comments, because it's the kind of information that people do think, well, I've got two valves, so I should put it in the middle, then they'll both be active. But if you think back to what we talked about to do with flow restriction and pressure drop, yes, you're going to open both valves, but you've got half the port either side. So neither valve is going to vent properly because you've restricted the flow. So yes, it should always be in either one valve or the other, fully seated to one side or the other, never in the middle.
Yeah, thanks, Stephen. So now I want to ask some questions, because you had a good point there. So if you just have a spring type, it's going to leak a little bit. You know what I mean? So you go up with your leak detector, pick it up, you blow it out, and then all of a sudden there's no leaking. I have this question from people. Well, if it's on the roof and you're outside and it rains or snow and that fills up with water, how does that affect the PRV if it's in the elements like that?
Yeah, so you should always avoid that, the valve filling up with water, especially, or snow, even worse. Because again, that's affecting the back end of the valve, the spring especially, and especially on straight through valves where it goes in and fills up, and you can get corrosion on the spring, which will reduce the set pressure. So again, you don't want to have any restriction on top. I've seen some people leave caps on the top, plastic caps, thinking they'll blow off in the event of a discharge, which they may, but if they're tight, they may cause the valve to suddenly reseat again and jam and things. And you don't want to do that. So ideally, you'd have like a little elbow or something on the top of the valve.
So that's a great one, because that's what I used to do. Like I used to,
a lot of people,
you know what I mean? Like I just leave the cap on there, red cap or orange cap. So you shouldn't do that.
You should only if it's literally light and it's just sitting on there, and you can
wind will blow that off, though. You know what I mean? If it's outside.
Well, exactly. So you're better with an elbow is the best. But yeah, if it's indoors or something and you want to protect from dust, and the cap on, not tight, but the cap's really just there to protect the threads in transit. It's not designed to. And although it's easy to think, well, the force of air or gas is going to blow this off. It's amazing what that initial moment of back pressure that it sees when it opens can do, and it can force the valve to close again. And then maybe the cap comes off, but the valve's already kind of stuck itself, and it gets into this weird. It's strange because it can actually affect the set point as well, which is it's almost counterintuitive. You think it opens and closes, but it kind of closes with such force that it bites into the seat more, and it can actually make the valve set higher.
Wow,
it's really strange.
See, I didn't know that. Okay, here's another question. I used to put, like when I was in the field, like, I'm not sure if it's leaking or not, put a balloon over it. Is that a bad thing to do?
No, not at all. That'll definitely show you if it's leaking, because if the balloon inflates at a rate, then you've got an obvious leak. In fact, when I first joined Henry, before we have the new test system we had at the moment, that's what we used to test valves and to see when they were opening, was to have the valve on the test rigs, increase the pressure, a little finger caught or balloon or something on top, and once it starts inflating, you know that the valve's lifted. Nowadays, we've got remote equipment and more high tech than that, but yeah, it's a valid way. It's the old fashioned ways. The easiest.
Okay, and another question. So if I like this way. What do we call this? Is it a trunk or is it a tree? What's this setup that you have?
Yeah, I've heard people call it. We call it a safety device assembly, but you could call it a tree.
I like that. Safety device assembly. That's perfect. So if I have a relief on this example, so we got the three-way valve, we got the rupture disc, we got the spring. You said if the rupture disc goes, it's a one-shot deal, right? You know, so that opens up. But if that spring opens up and then it seats back down, can I reuse that one that opened, or do you recommend replacing that one?
We always recommend replacing them. Again, something else that's kind of not a misconception, it's just something that's not really publicized a lot, is that PRVs are so sensitive. They're designed to be sensitive. That is the point, because normal valves, as you know, a non-relief valve will open slowly with pressure and then close slowly again. PRVs are designed in such a way that a small increase in pressure will lift the valve very suddenly, and that's all down to the internal aerodynamics and things. But once it comes back down again, because of this sudden opening, you often get a sudden closing again, and that the force of that reclosing action can affect the set point. So the valve will lift again, but you can't guarantee that it'll be within there's a plus or minus 3% tolerance on set point of valve. So you can't guarantee that after the massive force and all the debris that's probably been blown across the seat from the the little particles inside the system, that all affects the ability of the valve to seal. So you should replace it.
So we'll give an example here. So if just say it's 100 bar PRV, it opens up and it closes. By code, it cannot go open below 97 or 103, one or the other. That's the 3%, 97 bar or 103 or 1450 psi plus or minus 145 psi.
Yeah, again, with relief valves, nothing's ever simple. So there's a number of things a PRV has to achieve, pressure tolerance wise. There is a leak tightness test. So starting at the bottom end, there's a leak tightness test, which again, the standards leave it open to the manufacturer to determine how they do a leak tightness test and what pressures are involved. But they always recommend the API 527 standard, which is a seat tightness standard. So the leak tightness test that we do at Henry is at 90% of the set pressure. So up to 90% of the set pressure, there should be no leak on the API 527 method, which is basically the outlet of the valve gets connected to a tube, which goes into a beaker of water, usually. And then you look for bubbles at the outside of the tube. So at 90%, you should have no bubbles from the tube. Between 90 and the bottom end of your tolerance, which is 97%, bubbles would be allowed, but up to the set point definition. Now, again, set point definition is another thing that's different manufacturer. The code leaves it frustratingly open for different manufacturers to use different set point definitions. We use, again, using that method, a minimum of 1 bubble per second coming out the tube. We say that's when the valve's set. You get manufacturers that use pop as set, like the valve will be set when it pops. You get manufacturers that use first audible, which I find astonishing, that the first time you hear the valve is when it's set. So you actually have to be listening to the valve, and if that thing goes off, your bursted eardrum. But this is what some people use as the definition.
Yep.
So anyway, it has to be set within that plus minus 3%. That's when whatever your definition of set point has to happen within that plus minus 3%. And then 10% over your set pressure is the point at which the valve, it has to be fully open by then. Usually the valve's fully open before that. Ours typically get fully open about 5 or 6% above set pressure. So it'll start to bubble at within your 3%. And then at some point, around about 5 or 6%, it'll go bang, and it'll be fully open. But when they flow test valves, they flow test them at the 10%, because that's the worst case. So that's where the valve's flow tested and rated at. So that's your stages, if you like, of what a valve has to do.
I love that. That's huge. Like, I learned so much there. So now you, like, valve manufacturers, if one here, I'm here in Canada, it goes off here in Canada, and then it seats, and then it's depending on how fast it goes off, how quick the pressure goes up, and that reseats, and then you're out in New Zealand and it goes off. The same valve, same manufacturer, off the same line, the one beside the other, doesn't mean it'll be the same percentage afterwards. And that's why you recommend, every manufacturer I talk to, if the relief goes, that I've talked to, it should be replaced or repaired. I do have someone who asked the question, can these be repaired?
Yes, you can. Yes and no. Again, typically, nothing straightforward. None of our valves are designed to be repaired. So all of our valves are sealed once they leave the factory, and you can't replace the components. You do get typically larger industrial valves. When again in North America, the ASME code, it's an ASME. It's a UD up to. There's a stamp anyway that you can get to say that you're an official ASME valve repair maintenance laboratory, and you're a license to repair the valves. But with our valves, no, they're all one-use items.
Oh, that stuff is huge. So so if you're in the field and it does go, and you have a leak on that one side, that should be replaced. It's very important. And then, because the big thing is looking at that rupture disc. That should be one thing. Okay, if you have a leak, or you're picking up a leak, go look at the rupture disc if they're on there, and it'll give you an idea. You knew it leaked, or switch it over, ordered a new assembly, not the full assembly, but just the rupture disc and the spring, get the same ones. You don't want to oversize or undersize them. Get the exact same ones, order those up, and protect your customer, because this protects everybody and that system.
Yeah. Well, I should have mentioned, obviously, you can see them here, and you indicated it there, Trevor, as the rupture discs in our safety device kits come with these indicator gauges. So there's it's difficult to see on the screen, but there's a little yellow arrow there that will ping up to the pressure when it sees pressure. So it doesn't tell you how much the pressure is, but so you can see visually straight away which valve is gone. if without looking at the valve, without looking at the three-way valve to see like which side is line, you can see because the indicator gauge will be up saying there is pressure on this line. So it's an easy way to show which one's going.
Yeah. Yeah. No, that's awesome. I love this. Like I learned so much already.
Good stuff. That's that. Well, I've got a summary slide, but effectively just the key points that we talked about, which again, I won't go through them. Everyone can see the slides. But yeah, we talked through everything today and hope it was useful.
This was super useful for me. Like I think just that those troubleshooting points is very, very important because we like as technicians in the field, we don't see this a lot, especially if you're a service technician. We're going around, we're doing the leak detection. Okay, we've seen it. It leaked, it ruptured, it had a pop off, whatever it is. Our job is to make sure the leak is done because you always got to fix the leak. Pressure relief is a valve or if it's like a fitting that leaked. We got to fix that stuff and we repair it, and then we got to charge it back up. But diving in a little bit deeper and understanding why you're doing this. And, I like the rupture disc, understanding what that is. If it relieves, we know that spring is not the same and it's not going to hold the same as if it's brand new. So it's good to really understand that stuff. I love this. Anybody have any questions? Let me check through the chat. We have used them for decades, especially to reduce F-gas emissions. And of course, it's also lets you know the valve is lifted. Thank you, Stephen. Great sharing, Stephen. I really appreciate that. How can people get a hold of you, Jordan, and your team if they want to find out more about Henry Group and what you guys have to offer?
Sure. So our general, again, the website probably nowadays is the easiest way. We're on socials as well. I think we're on Facebook, we're on LinkedIn as well. You can get a hold of, just search for Henry Group Industries. The email address there is our general contact, contact.uk@henry-group.net. That's us in the UK. Obviously, the Henry Group is global. That's our phone number as well. You can get a hold of me directly. It's just my name. All our email addresses at Henry are just our names. So jordan.gronkowski@henry-group.net. If anyone's got any questions they want to get in touch with, that's fine, or I can put you in touch with. If I don't know the answer, I'll find the person in Henry that does, and we'll get back to you. But yeah, just check out the website. That's in the socials. That's the best way.
Yeah, I definitely think you have the knowledge, and I really appreciate you taking the time to share with us, because this is a topic that a lot of people PR pressure relief is boring. It's like, I don't need to know. That's the engineering stuff. But still, as a technician, we need to know this stuff. We need to have an understanding of every component in the system. When I'm doing CO2 trainings, because I've trained a lot of people, thousands of people in CO2 over the last few years, and you need to know every component. Just because it's not a component that's working every day, but it is working every day. It's in place there for those times that the pressure does build up, or you have a catastrophic event, or someone closes the wrong valve to open up. And this is not only for CO2 systems. This is HFC system, HFO system, industrial ammonia system. So understanding this is very, very important. Got a great question. During a commissioning pressure relief test, should there be a valve be replaced after test? Okay, so when you are doing a pressure test in a system, you have to blank off them or remove the pressure relief valves. Because here in Canada, the standard is that it's 1.1 times the design pressure. Same in the B52, the same with ASME 31.5. It has to be 1.1. So for an example, if you have a 1740 PSI, which is a 120 bar system, you have to do 1.1 times that. So you will have to blank off that. You have to actually remove it, pressure test everything upstream of that pressure relief above that pressure test. Because just remember, we're trying to protect the components in the system. So whatever that pressure is, all those components have to handle the pressure higher than the pressure relief valve. Anything you want to add to that, Jordan?
No, it's the same here. And EN 378 is our standard, and again, it says PRVs should be isolated or removed for system pressure tests. Because you're going to blow the valve if you do. The other thing, maybe to add slightly onto that, is a question we often get asked, and some people have the requirement. It's should I test the valve before I put it on the system to make sure it's working, make sure it's okay? And we always say no. You should never test the valve with a third party, because valves are so sensitive. It's very easy for you to do a pressure test with the best of intentions, but actually the test in itself modifies the set point of the valve, and you can get a false positive and a false negative. And as I said before, every manufacturer has different definitions of what the set point is. So you could be testing looking for a bubble when the valve from this manufacturer is actually set when you can hear it, or vice versa. So if you have to do a test on a PRV, again, the EN 378 standard says that each valve should be tested for seat tightness before it goes in the system. We, as a manufacturer, do that in-house, so you do not even have to do that. But if you have to feel like you have to test something, or if your notified body or whoever, your inspector wants to see a valve tested, it should be the seat tightness test you do, which is the 90%. You should never take it up to lift the valve. Certainly the Henry valves anyway, other manufacturers. Some you do get, again, industrial valves with lifting levers can be used to test them and things. But our valves should not be tested.
Yeah. So that's a great point. So 90% if you're doing that. So once again, if it's 100 bar or 1400 PSI, you'd go up to 90 bar, correct? So that's the max you want to do.
And again, you're looking for a leak as per the manufacturer's definition of leak tightness. So for us, it's that tube into a bottle and you're looking for 0 bubbles. Different manufacturers will have different definitions and requirements. So it's a minefield, especially from a end user's point of view. What do I do with my valve? But I can only speak for Henry, but for us, we do all the tests that you need us to do, or you need to have done in the factory. So when you buy a Henry valve, it's all been done. Yeah,
I got another good question here. Can you give me a thought? Is there a torque spec for installing a PRV onto a system?
It will depend on the thread. That's another good question, actually, but something we get asked a lot. Most of our valves, 99% of our valves, apart from a few specials that we do, are NPT threads, so tapered thread connections. Now, there is no recommended torque for NPT because torque is not a good measure of how well an NPT connection is engaged. So no would be the simple answer, because it's an NPT thread. NPT threads, it's turns past finger tight is the guidance. You can find guidance all over the place of the internet, and Google Google what it is. We've got some guidance in our literature as well. But yeah, you take it a finger tight, and then it's so many turns. I think it depends on the thread size, it changes, but it's between like 2 and 3 turns past finger tight, I think, for most thread sizes. If you have a parallel thread, which again, some of our valves have that for special applications, and some other manufacturers offer that as standard, then yeah, there probably will be a torque setting, but you should contact the manufacturer and ask them it should be in the operating instructions, to be fair, for the valve. But if you're not sure, just contact the manufacturer.
Yeah. Here's another question on it, because that was a great question. Do you recommend Teflon tape or thread lock on any of your valves, or just hand tighten like you just mentioned?
Again, we don't mind. Different refrigerants can react differently with things like thread tape. Is it 410A, I think, has an issue with PTFE tape. It can break up the tape. I might be wrong on that, and you'll probably correct me in the chat. So it's important to know what thread locking compound you need to use to match your system, if you like. When we test valves on air and gas at Henry, or when they go to the National Board labs in America to get tested, it's typically PTFE tape they get wrapped in. So there's no preference to thread locker. The important thing is to make sure, especially if it's thread locker compound, that you don't get any in the valve. Only apply it to the external male threads of the valve. Don't be too liberal with it. Be just a couple of threads worth, and tighten up, and make sure it doesn't go way in, because if it gets in there, it can go on the valve seat, which obviously can affect. Worst case scenario, it could stick the valve if you've poured it in there, which is doing. But yeah, so just be careful using thread locking compound that doesn't get into the valve.
Love it. Oh, Jordan, thank you so much for taking the time to hang out with us, share some knowledge. Next week at CO2 Experts with Chris Griffin from Omega Solution, we're going to be diving into some more technical CO2. Jordan, thank you so much, and I'll see you all next week at CO2 Experts.